think about this problem solve here. You could perhaps think in terms of cases. Well, first of all, let A be in G with A not the identity, say. One big thing to think about, very big thing, is applying Lagrange's theorem. 25 is 5 cubed. What are the possible orders of A based on that? They have to be multiples of 5. And if it's not the identity, it's also not 1. Lagrange is going to imply the possible orders of A are 5, 25, and 125. If A has order 5, we're done. So what if A has order 25 or order 125? Any ideas what if A has order 25 or 125? How can we find, so to speak, an element of order 5? Is there a way to do that using A, maybe? If A has order 25, that means the cyclic subgroup generated by A has order 25 and is going to consist of E, A squared, A cubed up through A to the 24th. Those will all be distinct. Give me an element out of there that's got order 5. A to the 5th's got order 5. A to the 25th would be E, and that would be the smallest positive power of A that gets you back to E. That's the same as A to the 5th to the 5th. Multiply the exponents. And yeah, that would be the smallest positive power of A to the 5th. That'll get you back to the E. i.e., A to the 5th has got order 5. Did I really prove that? Not super rigorously. I mean, it's pretty clear, I think, once you think about it. Technically, you could prove it with the fact back in chapter 4. I'm thinking of theorem 4.2. Now, again, chapter 4 is not explicitly tested on the exam, so you wouldn't have to quote this theorem probably. The theorem I'm thinking of is this one here, and this equality right there. In the case where n is 25, let A be an element of order 25 in a group, K be a positive integer like 5. The order of A to the 5th would be 25 divided by the GCD of 25 and 5. 25 divided by 5 is 5. So you technically could apply this theorem, but I think on the test, if I gave you a problem like this, you could just pretty clearly say, yes, the order of A to the 5th is 5. If A has order 125, then the cyclic subgroup generated by A has got 125 elements in it. And what do you think? The order of A to the 5th is 5 or something else? Not A to the 5th. That would have an order 25 in this context. A to the 25 has order 5, right? A to the 125, that's the smallest positive power array that brings you back to E. For A to the 25, 5 would be the smallest positive power that brings you back to E. It's going to have order 5. You were going to use this theorem. Now n would be 125. K would be 25. The order of A to the 25th would be 125 divided by, this would be 25. 125 divided by 25 is 5. So technically, yes, you could apply that theorem, but yes, again, I wouldn't expect you to remember the theorem number or something. It didn't have a name. So it's probably just a brief little argument about that I gave verbally based on these equations would be good enough. So we've done it. That does it, right? G's got to have an element of order 5. Lagrange for any non-identity elements, which there do exist 124 such elements. It's got to have one of those orders. It's got order 5, we're done. If it's got one of these other two orders, you can still make an element of order 5. Construct it.